So
Uh,
I'm going to talk a little bit about NEM, which is a project that I made. And so I'm a PhD student at the University of Tokyo, and I'm also the CEO, one of the founders of money transfer service, a digital money service for developing countries. And we're also probably going to be testing our work here in Japan as well. So please use us. We'll basically be creating something like PayPal in Japan, but something really useful, I think, for people. So NEM stands for New Economy Movement. Japanese direct translation would be Shinkei Zaiundo, and our homepage is at nem.io. So it's just a second generation blockchain platform, and we opened up on March 31st. Opened up. My English is really bad right now. So there's no mining, so the amount of the coins are in our currency is fixed at it's about 9 billion. It's actually 9 billion minus 1. It's 8,999,000,000. Yeah, so it's 8 and 9 nines. So that was chosen by some Chinese guys for good feng shui, I guess. Um, so the motivation to create blocks is from transaction fees. So every transaction has to have some ZEM associated with it for fees. The blockchain, everyone knows what a blockchain is. It's not just for storing transactions, it's also for storing any kind of data in a decentralized way. And that's what all that says. So why would we care about NEM? Well, NEM has a really easy API, so stuff like this, it's all just JSON, and hopefully we can play around with it some today, and I'll explain it some more later. We also have multi-sig, so if you create a transaction and it's a multi-sig account, you have to have all the signatory accounts sign off, and then this actually makes it really, really safe. So for our money transfer service, we're actually looking at making it so that if all of our private keys were hacked and leaked on the internet, no one could even steal any money because some of the keys would actually be on the person's phone. So they would have some of their keys to control their account, and then we would have the remaining keys for the signatories. And so all of it would just be really decentralized. And so that's one of the advantages of using NEM. Bitcoin has multi-sig wallets too, like Armory, but it's pretty hard to set up programmatically for programs to use. Basically, you have to have something similar. Yeah, it's really hard to get all the signatories to look for events and then sign off when needed. And it took a few days of programming to just to set up code that someone wrote to do that. so it's basically weeks of work to use multi-sig in a program for Bitcoin. We also don't have mining, so if you don't hate the earth, then you should use NEM. And we also used everything was done by test-driven development. So we have over 3,000 unit tests that we wrote, just four or five of us, and so it's been a lot of work. But it makes it really a lot easier to make changes to the code because you don't have to worry about everything to be totally broken. And also, all of our code is written to be really encapsulated, so that hopefully there's very few side effects elsewhere. The only potential places with side effects are in anything related to consensus. NEM is also working on what we call mosaic tiles. So these are basically colored coins. We study the work of Nick Szabo a lot, and he talks a lot about property tiles. And so we kind of thought about, well, we want just not property tiles. We want like smart tiles that can do computation and then contracts and then all kinds of stuff. So we kind of had this idea of combining different tiles together, and then what do you call that? You call them mosaic. So that's how we came up with mosaic tiles, and that's first version was just released on testnet today, but I have no idea if it's useful or usable. And then we are also working on domain names. So you can have 3 levels of domain names that you can register. And the advantages of this is that you can associate information with each domain name. And it costs lots of money to register a domain name, and typically people will keep it around for a while. They have to be registered, renewed every year in our system. So in systems like Next, you can register aliases, but once you register them, you have it for all of eternity. But we want to kind of make it like the internet domain name system. So that's why we have it expire every year. And so you can register that, and then you've got your domain name, and then you can associate mosaic tiles with your domain name, and you can also do things in the future. We want to also have like a reputation and weighting system. So it's impossible to do any kind of decentralized commerce or any kind of work with other accounts without any kind of reputation, because you have to know something about people and what they're like, what the probability is of them failing you if you're going to buy something. So we want to provide rating system, and that's an area of current research. We're not sure of all the details, but I think we're mostly decided. We're basically going to have 3 different types of reputation that we're tracking. So in Bitcoin, there's really little motivation to run nodes, and so in the past there used to be over 300,000 nodes, but now there's only like 5,000 in the world. Yeah, it's more than NEM has, but we've got about 100 nodes. But it's because of many reasons. One, the blockchain is so freaking huge. It's like 25 gigabytes or 30 gigabytes now, and so you can't even run it on like a cheap server on a VPS because those are limited to 20 gigs. So yeah, so that's one of the reasons. And then also people just kind of lost. So the first 2 dots are in 2013 during the big pump, and people just lost interest in it. I think people just thought that, hey, this Bitcoin, the rise and rise of Bitcoin, I'm going to be filthy rich and driving a Lambo in a year. But that's not what happened. So a lot of people lost interest. So anyway, there's little motivation to run nodes, and NEM will have the same problem eventually because as the blockchain grows, it'll take more and more resources to run a node. So we're proposing to create a kind of a high-speed network of nodes where you escrow 3 million Zem into, at the beginning it's going to be 3 million, into your account, and then you don't spend it or anything. And then that lets you join the program, and then random audits will ensure that you have a fast node, so you are able to, your ping times are fast and low latency, and you can deliver the bandwidth needed. Basically, we want to have a core set of nodes that are really fast and really, can do a lot of things. And in the future, we want to actually do things like make a fast distributed ledger on these nodes, and also use them kind of like as a computational cluster too, because these machines are going to be kind of high capability. And the motivation for setting up these nodes is not just transaction fees, but they're going to get, we set aside 2% of the currency for this program. So for 3 years or something, we're going to give a lot of money to these nodes. And then after that, to supplement, as the money runs off, we're going to add in some transaction fee sharing. So hopefully by then we'll have lots of users using the network in 3 or 4 years. And so there should be many transactions, and so the fees should be enough. Right now there's very few transactions, so the fees are not any motivation to run a node. But doing this should help us bootstrap the program, and hopefully we can get a few thousand really high quality nodes from that. But yeah, we'll see. I'll show the demo of our wallet later. So yeah, NEM is based on public-private key cryptography. Everyone knows this stuff. You just can sign or encrypt a message for B. That's a cool hat, by the way. You can encrypt a message for Mr. B and using his public key. And NEM uses ED25519. This is SHA-3, and it's a lot faster and than other algorithms that are used. And then also, there's SHA-256. Bitcoin, as I recall, hashes twice to prevent birthday attacks, and SHA-3 solves that problem, so we don't have to double hash, just hash once. And it's already, more or less standard. And when we went to program this, there was no implementation in Java, so we had to do it ourselves. So we did that and then tested it a whole bunch. There's a C implementation, so it's easy to test, and also easy to convert to Java. But yeah, if you want that curve, please use our implementation. Addresses in NEM, we don't. Unlike Bitcoin has just kind of long public keys, but NEM uses 40 length 40 alphanumeric strings that are kind of a little bit easier on humans. It's still really huge. This one I ran a vanity gen to say Makoto at the beginning. That took about a day. But this is base 32 encoded, and the first byte is the network byte, and then we have a 160-bit public key, a hash of the public key, and then a 4-byte checksum at the end. So you can tell if it's legit or not. The network byte just says what network we're on, because we have a test net. We actually, I think, have 2 test nets right now, and then we've got the main net. So it just keeps track of, so you don't accidentally send things to the wrong network. And we actually use the checksum to make sure that addresses are valid. So you won't be able to create a transaction and broadcast that to the network if it's not a valid address. So that's like some systems like Next and stuff. You can just send to random numbers and lose your money forever. So we wanted to make it a little bit harder, at least as much as we could, make it harder for people to screw up. This is what a NEM transaction looks like. We have many transaction types because of multisig. I'll explain it later, I guess. But basically, you can just make this JSON string and then curl that to a server, and then it'll broadcast it to the network. Whether it's accepted or not depends on whether it's legit. But you've got timestamp. This is the number of seconds since the creation of NEM. so, yeah. So at the NEM Genesis block, we call it Nemesis, but at Nemesis was the 0 time, and then every second past Nemesis, you get a timestamp like this. And then the amount is in Makotos is the colloquial what they're called, the subunit. But it's micro NEM, I guess. It's so you take off 6 decimals and you get the number of Zem for that. And then signature is the signature, and then the fees. I'll show the fee structure. That's kind of interesting. Yeah, I'll show the fee structure here later. So this is multisig. We support multisig accounts, and then testnet has M of n. And actually next week, I think we're gonna, maybe even this weekend, we're gonna release M of n on the main net. So this slide just talks about Nakamoto consensus. So proof of work is one implementation of that, probabilistic Byzantine consensus. So they've got mining. The real work that mining does is you've got like this probability curve, probability distribution across all the miners. You've got the distribution of computational power, and when you choose who will create the next block, you just sample from this distribution, and it probably looks a little bit more sloped in real life. But the key thing that you should realize is that to guarantee Nakamoto consensus, you don't have to do mining. You can just sample from any kind of mathematical distribution that is everyone has the data for, and then also that can't easily be manipulated. So if you can arbitrarily raise your score, then that's not going to work. So that's the inspiration of proof of stake, and stake just uses the account balance and samples from that. Basically, we proposed proof of importance, which uses information about the transaction graph. And I could spend a lot of time talking about all the details of that, but basically, the transaction graph information is one part of the score, and then the rest is a balance, but it's a weighted balance. We call it vested balance, and so uh, I'll show those slides, I guess. Let me unhide these. Got too many slides. So this is a vested balance. So when you receive some ZEM, you have 0 vesting, and then over time, every day you get 10%. The remaining unvested portion gets 10% vested. So you get this curve like this. So after about 20 days, you've got 90% vested. So it takes about a month to get fully vested, and then so this prevents you from just shuffling money around to boost your score, because the vested balance is used in the calculation. This just says that we use Aldlink matrix. We use the Aldlink matrix in this way. We cluster it using Scan++. Scan++ is a clustering algorithm developed by NTT, and it's an improvement over Scan. So Scan, I'll just explain it really quickly because we don't have. I guess I can't stand up. Okay, so you've got these clusters. I'll just no, it's fine. I'll just use my magic software. Okay, so you've got this graph, right? And in Scan, you have to look at every node in the Scan algorithm. In Scan++, you only have to look at the yellow nodes. So you look at each node 2 hops away from each other is the innovation. And so you look at this yellow node here, and then you see if it's core or not. And core just means you have some constant epsilon, and if the structural similarity between the edges between 2 nodes is above this epsilon, then it's called an epsilon neighbor. So it becomes your neighbor. And then if you exceed a threshold of epsilon neighbors, it becomes core. And if it's core, you create a new cluster around it. So that's what these dashed lines are. So the dashed line is the new cluster created around this containing the epsilon neighbors. So it's basically the structure of the graph is similar between this node and then these 3 nodes. So these are all put into a little cluster. Then the next node you consider, you don't look at anything directly connected. You go 2 hops away, so you come here. And then this is core as well, so you create another cluster here. And then you go 2 hops away to here, and then you kind of rinse and repeat. The last node is a special case. That's why you look at these 2. If you don't do that, you run into problems on line graphs where you don't you don't get the last edge on the line. I found that out. I think their paper actually didn't explain that correctly, but but we found it in our testing. So we create all these little tiny clusters, and then you go through at the very end, and then you merge these into big clusters. And so Scan doesn't do the merging. Scan just builds the clusters and grows them at each iteration. But the downside is you have to look at every node in the graph. So it's actually faster to just build a whole bunch of bad clusters and then just merge at the end. So merging is pretty fast, especially if you use fast data structure. So we used a sparse bit set to denote clusters for the nodes, and it's really fast. It's probably about 1,000 times faster than using like lists or something like that. So it is really fast. I like sparse bit sets. So that's that algorithm. Then the clusters are used in NCD aware rank, which I kind of described a little bit before the talk. So let's say you've got a graph like this. You've got really 3 kind of, all the nodes are kind of connected with edges, but really there's 3 different partitions that you can make in this graph, and they're 1 to 3, and then 4 to 6, and then node number 7. So you can say that this graph is nearly completely decomposable into these 3 different partitions, and that's what the NCD is. So it's the rank part is PageRank. So it's basically a PageRank that is aware of these partitions. So what we do is we take the clustering information from Scan++, and that becomes M in this in this is in matrix notation, so maybe it's kind of hard to see. Let me bring up our yeah, this is why I need a new computer. So that's why I bought a new computer today. I don't have it yet. No, my hard drive was full, and so it my index crashed. So anyway, that's not going to work. Anyway, so this is matrix notation. So hopefully everyone likes matrix notation because that's how I'm going to describe it. So the O is the outlink matrix. CO outlink, it's easy to say, and M is the multiple levels. So the it's really the NCD part and the NCD aware rank. So without the M part, you basically just have PageRank. That's what it is. And then what the mu and the what is that symbol? The N thing. No, I forget. I forget what this one is called. Anyway, I'm not Greek, so you'll have to forgive me. But what these two constants, these are just constants, and what they are is they define the kind of the teleportation. So in PageRank, the matrix for this to converge, because you have to calculate it via power iteration. For it to be guaranteed mathematical convergence, you have to have this matrix be it has to maybe I'll pull up. It's easier to see in the I really want to show you the white paper. It's actually called a technical reference. I have too many repositories. Okay. Great. So this is our technical reference, actually. So if you've got time to read a 58-page paper full of math, then please look at it. Great. Okay, great. So anyway, this is what it looks like actually in normal iterative form that you could actually program easily. So the R just denotes the current iteration, and R minus 1 is the previous iteration. And so you've got the outlink weight from the previous iteration, and then the M, the interlevel weight for the current or for the previous iteration. For each account you're going through, and then you're weighting that by these constants. So the constants actually that we used are basically this equation here has to be irreducible and column stochastic, the matrix, when you put this together. And so you basically have to have a non-zero probability of each account outlinking to another account. And that's what these constants do. So they just kind of say, I think the numbers that we used were 0.75 and 0.1. So you've just got basically a 15% chance of randomly jumping to another account is how it works. So that's PageRank does the same type of thing. And actually we're exploring if that's really needed. So there's some situations in NCD aware rank where you don't have to have any teleportation. And the advantage of that is it'd be harder to manipulate the score because teleportation gives kind of a baseline score to even really stupid accounts that don't really have any links. And so it would be nice to not have to worry about that so much. But to prevent manipulation in NEM, the importance score is calculated this way. So just walking through this. So V is the vested balance, and this is the weighted net outlinking ZEM. So if you send 2,000 ZEM and you receive 1,000 ZEM, and then of course all that's weighted, but let's just say that they're weighted the same, and then you've got a net outlink of 1,000. So that would give you like plus 1,000 here. and then that's just added to your weighted balance. And this can go negative. So if you actually receive more than you give away, then it will actually be subtracted from your balance, and so it will lower your score. But you can't go below 0 because we're doing this max. And then this is the NCD aware rank, and this is weighted by WI, which is which is pretty elite. This is about 13%. So the reason we weight that is because the teleportation makes Sybil attacks, Sybil manipulation a little bit possible. It's harder than in PageRank, but it's still possible. So for security of the system, we limit this to about 13% of the score. And then at the end here, this is Chi, and that's the graph structural weight. And this is 1 if your account is in a cluster or not, and if it's not, then it's 0.9. So you basically get a 10% hit in importance for not being in a cluster. So you want to be in a cluster. So you want to transact with at least a few different accounts within a month so that you can get into a cluster. And if you're not, then oh well. I mean, you're not important. Sorry. So we did a little bit of tests comparing to proof of stake, and this is actually on the Bitcoin graph. So in October of last year, we downloaded the Bitcoin blockchain at 23 gigs. And then we used just a subset of that from October. So people who transacted in October, we took 55,000 accounts. And then we ranked all the accounts from 1 to whatever, 55,000 or something. I mean, if they had the same amount, they would get the same rank. So, so that took care of that. And then we looked at what the increase or decrease was if it was in stakes, based by stake or by importance. And the poor half of accounts increased about 2,800 ranks, and then the rich half went down almost 3,000 ranks on average. And then the average rank for everyone was they went down about 65 ranks, 67 ranks. And so basically it just kind of levels out the rich and the poor a little bit. And you can kind of see this in this normalized graph, where on the left-hand side you've got proof of stake, stake weighted, balance weighted accounts for the sizes, and then the right-hand side is importances, and they're log scales, and they're normalized, so it's really hard to compare the two. But these were normalized such that all the scores will sum to 1 on both of the graphs, so you can kind of compare them. And you can just kind of see that the importance scores are on average smaller. There's not as many big nodes, basically. So people are more equal. But still, this is log scale, so there you go. Am I out of time? This is how block score is calculated. It's the block difficulty minus the time from the previous block. So that's the score. And Koi is actually used to create blocks in this way. So I was kind of describing this earlier already. So you've got hit and a target. You want if the hit is less than the target, then you create a new block. And the target is defined as the hit is the kind of just a random number. So you've got the generation hash of the previous block and the public key of the account of your account, I guess. I'm not sure if it's the block creator's account or your account. I'd have to look at it, but if it's written that way here, it's probably your account. And then you hash that, and then that gives you just a 256-bit random number. It's a random number, but everyone in the blockchain can verify it because they have this information. They know what the public key of the account is. They know what the previous hash or block hash was. So that just gives you this huge random number, and then you want to see if your target is going to be greater than that or not. So the target is just calculated by, you've got 2 to the power of 64 just to give you a good start, and then B is just the importance of the account, really. Like I said, there's about 9 billion them, so that's how the That's why that constant is there. And then D is the difficulty for the new block, and then T is the time since the last block. And the difficulty for the new block is calculated this way. So you've got the average difficulty for the last 300 blocks. I think 360 blocks is what we use. And then you've got the average time between blocks for the last 360 blocks. And that gives you D and T. And then you just see how that varies from 60, because 60 is the number of seconds that you want. And then you don't want to change the difficulty more than 5%. So this is actually what difficulty looks like over time on the main net. And you can see that too on our block explorer. Nimbix. What? There you are. So this is our block explorer Nimbix. It's at chain.nim.ninja. And if you go to statistics, you can see the difficulties here over time. It just goes up and down. It goes up and down. Why does it go up and down? Well, some nodes come on the network, some nodes go off the network. That's really the reason, I guess. And you can in the calculation we use about 360 blocks, I think. So you can see what the block time averages, and you can see it's really close to 60 seconds. And if you average by even more blocks, you can see that you've got a pretty good amount. Actually, today is a little bit more volatile than in the past. Well, I guess it's all about the same. Sometimes it's really, really close. So this scale is not so big, so you can see that it's really pretty good. Okay, so that's the difficulty. And that's just done every block, and then we tried to keep the variances between blocks as small as possible. That's mainly what I want to say. When you get data from another peer, if the block score of the peer is higher, so if they have more blocks than yours, or if the block score is higher, then you replace your blocks with theirs, and then you take up to 400 blocks at a time. And then you can also do things like blockchain unwindings. That often happens. This is an Ethereum meetup, I think. And so Ethereum forks, I think, constantly. And so those are called soft forks. And for different reasons of data propagation or all kinds of reasons, you can have soft forks quite recently, where you have two valid chains. Maybe one will just have a slightly higher score than the other. So eventually the network should converge to the higher chain. And so if you find a peer that has a better chain than yours, then you delete your blocks and you replace them with the peers. And that's blockchain unwinding. And we actually have a limit of 360 blocks, so 6 hours. So after 6 hours, any transaction that's in a block is never going to change from that blockchain. And in coins like Bitcoin, you can go back to the 2008 or 2009, I guess, and undo it all if you had a supercomputer. But NIM, it's fixed. And but before that time, you can still get soft forks. It's still possible that the chain could unwind. So if you're selling a Lamborghini, you might want to wait 6 hours.
What is a score?
The block score is done this way. So it's the difficulty minus the time from the previous block.
So how was the 100 soft forks at that time?
Hmm?
In 6 hours, 100 soft forks. Assuming there are many soft forks. The current 6 hours. Then I don't know which soft fork I mean. So so in that case, what kind of sequence will happen?
Well, you get the chain data from the peer, and so you can calculate the score just by summing up the score of all the blocks. That gives you the chain score. So if you have lots of forks, then well, then something's wrong. But but it is possible that you can get forks for that last 1 to 2 blocks in depth, and then what should happen is that if that data should propagate through the network if the network is healthy. The peers should just be talking to each other and finding out what the best score is, and the score can be independently verified.
Yeah, if I'm in the yeah fork A, you in the fork B, then I'm going to fork B, then my spending is not written in history.
Yeah,
So it can
if you're
be
on the
yeah.
lower fork, yeah. So
So do you want to delete the soft forks or
yeah, you have to delete the data. So uh, the same transaction can actually be in different forks at different times, but typically the way you would get a fork happening would be two people create a block very close to each other, and then it takes time to propagate it across the network. So so you have two valid chains that last for kind of a brief amount of time, but one block is going to be better than the other because the person created it before the other person. And 51% of the importance, that doesn't matter, I think. For soft forks, it's not really a problem. Now, if you're going to do an attack like creating a private chain and then keeping that secret and then working on that chain with your importance, and then you would have to have a large amount of importance to be able to create blocks. You'd have to have over half the importance to create blocks that would quickly. Well, you'd have to have a lot more than half to be able to, in 6 hours, create a private chain and then do that. But you'd have if you were to get that much importance, you could actually create a chain in private and then release it publicly, and then everyone would take that chain instead of the other one if it's within the 6 hours. So after the 6 hours, the peers will never release their data. So if you actually had forks happen beyond that depth, then then you've got a hard fork. So you have to decide which one you want to join, and that's not pretty. But yeah, you should never have that happen actually.
yeah, if I want, if I want to do the finning attack, yeah, zero confirmation and the double spending to the merchants,
Yeah.
then how many times the merchants should wait?
Okay, so soft forks of maybe 2 to 3 blocks are not very uncommon. They happen sometimes, a few times a day maybe. I haven't really looked at the statistics. So if this is a hackathon, so we could even try to plot or try to get that data in real time. It doesn't last anywhere because that data is you replace the old chain with the new chain, so you don't know exactly what the details are unless you can look at the logs. The logs will tell you when you're replacing data. But typically, yeah, like 10 confirmations about 10 minutes would be really safe for anything. And if you it's probably safe even to accept things instantly. The biggest problem is you want to make sure that a transaction is confirmed in a block. So double spending is possible, yeah, if a person's mean, but a more likely situation is that if someone's at a store and they buy something, then maybe it just gets unwound. So you want to rebroadcast the transaction. So you want to have that byte array so that you can rebroadcast. And most transactions have they have a default deadline of 24 hours. So if they're not in a block within 24 hours, they get deleted from the unconfirmed cache. But if they until then, you can try to rebroadcast if you have the data. But that's about that. So this, yeah, having soft forks of 1 to 2 blocks is is pretty common in any of the networks, even Bitcoin and things like that.
うん。
Uh,
そうだ。
in Ethereum, I think not having forks is uncommon, but because they have a 12-second time, and so you can't propagate the data sufficiently across the network. So
う
they've
ん。
got lots of forks. I think they're called like uncles or something. What was it like
sdev.com
stats.sdev?
sdev sdev.com
Ah,
S
S. Okay,
ETH.
okay, okay. Sorry about that. Okay. Yeah, this is really cool, by the way. But yeah, uncle count, right? Isn't that like aren't the uncles like related to the soft forks or something? They're like a transaction that I forget the definition of uncle. Does someone know here? No. Yeah, so Ethereum created too much vocabulary, so it's hard to keep track of. But as I recall, the uncles are like transactions that were kicked out of blocks in soft forks or something like that. I don't know. But anyway, if you look at this, there's a whole bunch in like every block.
Yes, scale block.
Yeah, maybe. Yeah, that's
Yeah,
that's
yeah.
what it was. Okay. Yeah. So it's that's why you don't want to like look at this average block time 8 seconds. So in a network the size of Bitcoin, you can't even propagate transaction data that fast. Anyway, it's a hard problem with this type of blockchain technology, and so
The long range attack doesn't problem. The problem is the short range.
yeah, long range attack would result in a hard fork, and
So they
so
make a private chain and then upload it. They rewrite the entire history. I assume it's the main
well, but
attack.
nodes wouldn't sync with you. I mean, new nodes would possibly sync with you, but existing nodes wouldn't replace their data.
Mm.
So basically, it would be pretty hard to set up a whole bunch of nodes. Maybe it's possible, but I think most if you had invalid data, of course, then I mean they have to be valid blocks. So
Mm.
you can confirm if the blocks are valid or not. If the person was supposed to create them or not, you can see that, and so you'd have to do a lot of mining. Well, it's not mining, but you'd have to. It take lots of time because it takes time. Time factors into the block equation. So I don't think it's very easy to do. You could try it. One of the things that we do is we use Eigentrust++, which is a peer-to-peer network reputation system. And so let me unhide some of my slides. So this just makes things safer. So every time you communicate with another node, you've got 3 different possible outcomes. You've got valid, the data is valid from the node. Neutral is just they've sending you the same data that you have already. You already know it's correct. So it's nothing interesting. And failure is they actually send false data or incomplete data or some kind of. I mean, it doesn't have to be malicious. It could just be bad network. Like maybe someone's using SoftBank as their internet, and so they cut off all the time. So for Eigentrust++, we only care about valid and failures, and so it's taking a long time to explain everything, so I won't explain everything. But feel free to look at our technical reference. But basically, you start out with an initial trust vector and all the nodes that you know of. That's just everyone gets the same amount of trust. And then you look at your interaction with the node, how many valid and how many failures you have with the node. And then you ask each of those nodes to tell you about those other nodes. And then you compare what they say about the other nodes to see if someone's lying. And then you take what they say about the nodes and you factor that in. So you use those 3 pieces of information. And this is done iteratively over the matrix of local peers. So this is a power iteration. And that converges to a vector across, well, an eigenvalue across all the peers around you that corresponds to trust. And so that's why it's called eigentrust. And eigentrust++ just has a little bit of improvements that make it harder to spam. And we did some. Actually, in our case, it's much easier than the regular eigentrust case because we can tell if data is valid or false, just because everything is, you can confirm it cryptographically. So if someone sends you fake transactions, that's going to be pretty easy to check. So you can't actually fake transactions. The worst you can do is censor people. But even just sending a whole bunch of trash data around will slow down the network. That's the main reason why we implemented this system. And in our simulations, we got something like this. So if you've got on the x-axis, you've got the percentage of malicious nodes on the network, and then on the y-axis, you have the percentage of failed calls. And then so this would be interactions with the node, trying to get data, stuff like that. So even with 90% of the nodes on the network malicious, you only have 3% of the calls that are failing because the data is being shared, so you know that these nodes are bad, and so you aren't even bothering to connect to them. And that's when the bad nodes always tell lies. But what's harder is when they tell lies maybe 40% of the time, and then tell honest data 40% of the time, and then 60% of the time give fake data, and then also feedback from the nodes as well can be lies. In this case, if you've got 90% of the network malicious, then maybe almost 20% of the calls fail. Still, you've got 80% of calls that are successful, even on a network that's really, really bad. So yeah, system like this can be really helpful, I think, for helping the network to be more secure, harder to spam, and more reliable. So in AI, we typically we often have what's called the knowledge pyramid, or what KDV pyramid, and what this has is at the bottom you've got data, and then interactions among the data builds up into information, and then interactions among the information leads to new insights, and that's knowledge, and then interactions among the knowledge builds up into a higher level, and that's wisdom. And related to crypto, account balances and just public keys, stuff like that would be data. And then relationships among the accounts, like in transactions, that's information. And so that takes you to crypto 1.0, so like Bitcoin and things like that. And then maybe you take the transaction information and then you can build up things like that. So event-driven, at this type of transaction, you do this type of events, so stuff like that. That actually builds up into knowledge, and you can do things like computation and distributed applications. And that's crypto 2.0. So that's where NEM wants to be. That's where Ethereum wants to be. I don't know if there's any. There's a few other projects that are trying to do similar things, but I don't know how serious they are. And then if you can take all these computational programs that are distributed, maybe you can do something more that's intelligence. So that'd be crypto 3.0, but I have no idea what that's going to look like. But Skynet, I think. So it's probably more like, well, machine learning would be one step. That'd be like 2.5, I think. So doing things that can predict human actions and then do some kind of change or action to change that person's actions. That would be kind of 2.5. 3 would be actually changing the network itself and recreating itself, probably. Anyway, so that's the idea. So at the end here, I just wanted to kind of outline a vision for them. So maybe at the Tokyo Olympics in 5 years, what kind of uses can this technology have? How can it help people? So one idea was to have something like a NEM phone, and so where all the calls and data would be encrypted. So that's technologically not so hard. But then also on the blockchain, you would have your passport information just on the blockchain. You don't have to actually carry anything. So if you go overseas to go see the Olympics, you only need your NEM phone. You don't need all these government documents and cards and stuff like that. And another idea was maybe have the NEM nodes give free Wi-Fi so that anywhere in the world you can have a free internet access. And even if you went to Japan from another country, using like a decentralized exchange in the background and maybe smart contracts, you could automatically change from your country's currency to Japanese yen on the blockchain, and then buy things in Japan without credit cards already kind of do that, but credit cards do that because they're huge corporations that have like liquidity suppliers and some kind of, they're holding lots of funds in different currencies, and so without doing that, maybe if you could have a peer-to-peer market that would allow that, and maybe at that time the Japanese government doesn't need any kind of taxes or taxation. You can get money by putting Japanese yen on the blockchain and then using a smart contract so that every time anyone sends Japanese yen on the blockchain, they take out a small amount on as a transaction fee. And so actually in NEM we support this. Or will, and I don't know if it's in the current version or not of our mosaic tiles. So the owner of the tile, or the person who creates the tile, they can create what's called a special transaction fee, where every time that tile is sent, someone has to give a special fee that comes to you. So it's made for governments and corporations and stuff like that who want to create a currency on the blockchain, and then I think that'd be in a way nicer because every transaction, you don't have to worry about taxes or money laundering because you already it's built into the system. You don't have to do anything else. So it would save a huge amount of money and time for governments and businesses, and it would make society a lot safer too. Also, you could put prescriptions for medicine on the blockchain. So that's really quite simple, I think. Just use public-private key cryptography to verify that a doctor gives you a prescription, and then put that in the chain. So in Bitcoin, every account is kind of, every time you send money, it changes. But in Ethereum and in NEM, every account is fixed. It has an ID and an index too. So yeah, you can actually, if you choose to, you can always use the same account, and then that builds up reputation. You can know who that person is. Yeah, you could. One interesting idea for Internet of Thing IoT application would be a M of N multi-sig lock. So to open like a vault or something, you have to have like 4 or 5 people sign off on the blockchain. And we were joking about how that would make every James Bond movie obsolete. So you can imagine him parachuting down into a castle, and then he can't pick the lock because it's multi-sig. So something like that would be really easy to do, but it also could be very powerful if it's done correctly. I like the idea at the bottom. So you could have toilets that connect to the blockchain, and then automatically could do processing on your feces to tell about your health and stuff. So it's actually really valuable information, and you could find out diseases and stuff before you really get into a big problem if you did that. Using private or cryptography, you can send that information confidentially to to your account that's detected via NFC or something. So there's actually, I know of a few different companies using NEM or building on the NEM blockchain. One is a crypto exchange that's going to be announced shortly, and that's going to be between fiat money and Bitcoin and NEM, or ZEM is our currency. So so people will just be able to do that. Now, what the big innovation is it's not a GOX style exchange where you give all your money to them and then you kind of trust them. Instead, every person will have this money, even Bitcoin, in their NEM wallet. So we'll take the Bitcoin, we'll put it on the NEM blockchain, and then put it in your wallet, and then you can, when you want to trade, so create a bid or ask or whatever, then you can put that into or control of the exchange's account, and then they can, trade, and then after the trade goes through, it goes back to you. So the only risk or time where there's a risk is when you're actually doing the trade matching, because the blockchain is too slow to do decentralized trade matching. One is my service for sending money internationally, and then another one is PhotoMeet. PhotoMeet is kind of like an Instagram type of app, but you can buy and sell photos. It's kind of also geared towards professional photographers, so I think they're trying to bring together both professional photographers and kind of amateur people, just social media and stuff. Yamphi is a social decision making app, and I don't know when it's going to be brought into life. I don't have enough time or money, so. And that's maybe all I'm going to say. I don't really want to go into the details of my company at this point. So we have this cool site called nodeexplorer.com. So Node Explorer shows all the NEM nodes, unless it's down. Anyway, we also have another site called Block. Okay, so there it is. It's coming. There's also blockexplorer.in. Great. So this is another type of block explorer that someone created. So you can see nodes on here as well. So every NEM node is booted with a private key, so it has an associated address. You can see the nodes that people have, and then there's different things like a rich list graph. So this is probably easier to see. So this is the distribution of accounts in NEM. So these two are Poloniex, the exchange in America. They hold about 5% of the currency. And then this is I can't read what that says. That's also Poloniex. Wow. Okay, so they've got like a couple cold storage accounts and stuff. And then some of the bigger ones around here are I don't know. This is Bittrex, another exchange. I'm probably somewhere around there. And then you can see lots of people have about the same amount. So this just shows the distribution of the currency is very well. It's fairly egalitarian, maybe. It's pretty good, I think, compared with a lot of other currencies, especially Bitcoin. Even in Ethereum, I think 100 addresses have over 70% of the currency, I guess. So it's not really that well distributed. But any kind of system with wealth is going to be Pareto distributed. So that can't really be helped. So Node Explorer looks kind of dead right now. Yeah, it's dead. Either the network is completely dead or Node Explorer is dead. And my bet we can find out by going to the official Block Explorer at chain.nem. And we can look at nodes. So if all these, okay, so it looks like the network's not dead. So there's 77 nodes online right now. And the IPs are partly abbreviated. So Block Explorer or Node Explorer actually, when it works, will show you the unmasked IPs. So you can just go to anyone's server and connect to it, and that's actually safe because when you're signing transactions from the client, it doesn't send the private key. It signs it locally and then sends the already signed bytes to the remote node. So the remote node never needs your private key if you're not harvesting blocks. So the worst they could do is send you is censor data, so just not send you data. They can't create fake data because you verify it. So it's actually pretty safe. I'm not sure if the client verifies all the data actually. So it is possible that maybe a node can show you some fake data, but they can't actually steal any of the money that you have. And that's that for that. Then we've got the API at bob.nem.ninja/docs. This is from 13th, so it's not totally new. And it's really long. We've got a lot of stuff in the API. You can do lots and lots and lots and lots of stuff. So it's a lot of stuff. So you can do anything basically. Let's see. So one interesting thing is retrieving historical information. It says historical, but that can also be, you just say what the block height is. So for any block height, okay, so yeah, okay, it's great. So you say an address, so the address of an M account, and then you say the start height and end height for the blocks, and then increment could be like if you want to do 100,000 blocks, instead of doing all the blocks, you can get every 10th block or something. And then what it'll give you is oh great, you can actually see the see what it looks like. This big Alice 3 is a live node on the mainnet, big alice3.nem.ninja, and that's run by one of the devs. So you can go to there, and you can actually see in the browser. Yeah, you can even see that that's the data, and you can see start height and end height is there. But if you want more, then you could say I don't know. Only up to 1,000 data points. Oh, well. So you have to do it 1,000 at a time. But what it gives you is it gives the balance of the person. So that's the total balance, and then you get the vested balance, which is vested, like I was saying, and then the unvested. So these two should add up. It gives you the importance score of the account, and then the page rank. So the page rank is the page rank, well, it's NCD word rank in the transaction graph. So we actually have that information as well. So if you want to use it in something, so that will give you information about accounts. You can actually get a list of accounts by going from the first block. So you'd have to get the transactions. So you want to get the transactions from the Nemesis block. No, that's not what I want. Yeah, the first block. So the first block sent out transactions to all the initial accounts, and then well, it created all that, but it sent it out to about 2,000 accounts or 1,800 accounts or so. So we just got a whole bunch of people to join on the web internet forum, and so they joined. Most of them don't care too much about NEM, but there's some good people around. So you can get all kinds of information. So you can get the current height of the blockchain. Okay. So if we go to Big Alice 3, well, I can't type. The current height is 157,388. So you can get score also for Alice's chain. So Alice has a score of this. Seems legit. So you can get all kinds of information about the blockchain. You can get the last block here. So if you want to do something like a chain explorer, then you would want to get this. that gives you the timestamp of the block and then the signature. This is a little bit hard to read, but it looks like this, formatted nicely. So it'll give you transactions just in the JSON array, and then each transaction, there is a transaction here. Great. So it has the timestamp of the transaction. So that's one advantage of NEM is all the transactions have timestamps. It has the amount, the signature, the fee paid, who received it, and then the type 257 is transfer, so transfer of Zim. And then if there's a message, it's written here, but there's no message. And yeah. And then you got the version number. This is for the mainnet, and then you can see the signer here. Interesting, great. So it seems to work. So that's just some of the information that you can get about blocks. If you want to get nodes, you can find out what nodes Alice is connected to by getting the active nodes. Here it is, peer list and all. So you can, if you want to know about who Alice is talking to, you can get the list of Alice's peers. So Alice is very popular. And you can there's lots of information about the peers. So there's the public key, the endpoint. You can find out what operating system people are using. So this person's Oracle, Linux. They're running this version of the software. Stuff like that. And you shouldn't always trust it because they can write anything they want. Especially for software. If you look at the nodes, the icon is the operating system. They've got Windows and there's one Mac.
This one is automatically added, or someone who reports I have made the node, then please add me.
No, the nodes just talk to each other. So that's how they kind of find. So Alice has a good reputation. So Alice is talked to a lot. But you can see that you can say any operating system you want. So Alice actually says her operating system is. Let's see what Alice says for her operating system. So node, you can just go to node info. So node/node/info. So yeah, so she's saying this just Linux. Hi, I'm Big Alice 3. But you can write all kinds of things on there. Network ID, interesting. Features 3. I don't know what the features means. But maybe there's some features. The number of features the node has. I don't know what that means. There's no documentation. But yeah, so that's the type of information that Alice and all the nodes has. So if you want to hack something together just about network statistics, that's one way to do it. Getting a block, requesting parts of the blockchain. Okay, so if you want to get some blocks from people, great. Use block and then at. Then public is it has to be post. Not sure why that's set to post, but anyway, it's too hard to get from the browser. If you know the block hash, you can get it easily using just the get. Yeah, okay, so that's what it can't be done. But programmatically, you can do post to that, and you can get the part of the blockchain. So I think the reason it can't be done, I don't know what the reason is why it's not a get, but anyway, so you can get the hashes of the blocks here, and then also transactions and signers and all the block information. So you can get all the block information from that way, actually. But so basically, all the data, I should show the client actually. So all the data in the client is supported via the API. You can actually download the client from bob.nim.ninja, which is a great URL, and I can't type. We have installers too, but you have to have Java 8, SDK 8, not the JRE. But it's a lot easier to set up than Ethereum, I think. Okay, so no space left on device. My hard drive is full right now, so I can't run this. I'm running too many programs and probably kill some things.
Could I ask about
Maybe we should show your client.
NIS is not available.
Yeah, you can. You start NIS, but it's okay because you can do remote server to big Alice. But your NIS works anyway. But now you're on Alice, which is safe as long as you don't harvest. Harvesting requires your private key. Okay, let's go back to localhost. So localhost, yeah, your node is booted. You can go inside the wallet.
If I'm on the harvesting on Bob Ali 3, then my private key is a secret key.
Yes. If you're not
signature.
Oh. Okay, so it's still beating up. Oh, okay, so that's what it's saying. What it's saying here. Still be done. But you can also use lots of different languages as well. Just have 17 languages, I guess. But let's check out Big Alice. Great. So this is a new account, so there's no money here. But if you had money, you could type in recipient's address here, and then you can type in an amount, and then you could type a message. You could encrypt it if you wanted to. There's no money here, so you can't do anything. But what's interesting is maybe the transaction fees in them. So if there's no, do you see the fee? If you're sending nothing, you have a fee of 12. If you send 1, you have a fee of 11. 2 is 10. 200 is 4. So it's spam protection. So you can't just send like 1 Zem and and then kill the network. But what's interesting is, so 100 is 4, but 1,000 is also 4, but 10,000 is 8, and then 100,000 is 60, and then it goes up, and then it starts to level off. So if you keep adding, it doesn't really go above a certain amount. So it's a progressive fee. So fees are a form of taxation in a way, because you're taking from some of the money and you're giving it to other people in the network who are harvesting. And so that's what the fees are doing. So in a way, economically it's somewhat interesting model. But you're redistributing the wealth a little bit while also providing spam protection. But the price of Zem is so low that it doesn't matter. Of course, it's still less than a penny. So, but yeah, I mean, spam protection is important. Anyway, that's about all I wanted to say. So maybe if people want to build something, we can build something, or we could
And
go
yeah,
drink beer.
or the QA.
Does
Is
anyone
that
have any questions? 日本語でも大丈夫。
Let's begin.
Too many questions.
For example, I understand a lot of the being able to communicate.
Yeah.
But
What's the fee calculation? Well, there's a.
please hold the mic next time. Yeah. Yeah.
Yeah, it still won't load. Okay. Let me. Let me open up our awesome technical report. Let's see. I actually have it in my slides that I just had open. I hit the slide, I guess. So I've got too many. Okay. So this is the fee. How fees are calculated. So, ooh, that's cute. Let me unhide this. Okay, so it's progressive fee structure, and so just for sending transfers without a message, it's 10 minus the amount, and then well, this was the original. Well, this was the original way. I think it was raised to 12 for the current version. But if the amount is less than 8, or if it's less than 10, then you use this arctan function. So you've got the amount divided by 150,000 and multiplied by 99. And this, I think, was just kind of eyeballed that looking at the curve by the person who created it. So we had thought about maybe making fees dynamic based on the amount of transactions on the network and stuff like that. But we figured that would be too hard for companies using them to kind of find out what the transaction fee is and then work that into their calculation. So instead, we just made it this fixed equation, which I think we changed the fee structure since this technical report was written. So that's why it's a little different. Now, if you have got a message, then you have to pay by the message length, and that's in bytes. And so the longer the message is, the more you have to pay. Messages are fairly expensive, actually, because they bloat the chain. So I don't know. Can we see if it is here? Okay.
That's why.
Yeah. It is 10, but we had a message inputted, and so that's why it went up. So but if you type up a whole bunch of text, hey. Okay, so it can for reasonably sized message, it's about 20 them. Yeah, and a lot of exchanges use the messages. So Poloniex, Poloniex, you just saw their big bubbles. They've got everything in like 3 accounts, so they don't know which portion is yours, except in their database. So when you input money into there, they give you a little string, and you put that into a message, and that's recorded on the NEM blockchain. And you can actually see on the Explorer, you can see a lot of let's see.
This written where on the blockchain or message.
Well, yeah. So maybe if we see this here. So these are some messages. Oh, okay, so this is like what the Poloniex. I think this is Beater. The Chinese. Oh, this is Beater. That's cute. They're paying like 10 zem to to put that on there. But anyway, that's what they do. This is Bittrex. That's cute too. Invoice number. Okay, so this is like a what would happen in the real world. And yeah, these are all Poloniex. So people with inputting money and then also withdrawing money. So here's one. Hi, Jeff. So people, yeah, most of them are just the exchanges. So you can see that there's no one really using them except for just trading. So which selection man current imagine existing? What? That's crazy. Maybe someone was sending a password to themselves or something. Sometimes people do mean to encrypt something but don't. Welcome to NEM. Also, please join Slack. So there's like a lot of stuff. Yeah, someone wants to make a NEM Docker. Anyway, so that's the type of messages that we have. But yeah, it's a really complex system, as you can tell just by looking at our like 50-page technical report. And the technical report is really long, but it's actually written very sparsely. Like we don't, there's not much fluff here. We try to be very to the point with everything. So it says like how everything is done. So it's pretty technical. So we talked about cryptography, the curve that we used. So it's actually really easy to read, I think. We've got fun little quotes at the beginning of each chapter. So this is from Jack Kerouac. But I don't know. We had a lot of fun making it. We actually wrote this 58-page thesis in just like 3 weeks. But we have a spam filter too. So if for unconfirmed transactions, that one account just can't fill up the transaction cache, and so we use an account's importance to kind of weight whether they get into the account cache or not, or how many transactions they have. And we've got the, depending on how full the cache is, the share that you can have the cache changes along this curve. So we like curves. So this is for the transaction cache. So to make sure that no one account can spam, each account has what's called their fair share of the. Well, this is for the effective importance, and then the effective importance is used for filtering a transaction to see. Okay, so we've got the fair share here, and then it's basically a function of the importance. So this is how many transactions you can have. So if you have a reasonable importance level, then you could have like 6 transactions in the cache, maybe. I think that's what this is saying. And then as your importance goes down, then it goes down as well. Anyway, okay, so this is at 1 per milli importance. So as the cache gets fuller, it goes down. So at this importance level, you can't put any transactions into the cache if the cache is like 80% full or something. So that kind of gives priority to people who are more important. Transaction fees also make a
How about the smart contract thing?
oh, so
Yeah.
that's not
The
even.
vision you thought about what is a smart contract.
Yeah, so yeah, we have lots of ideas, and actually, I didn't talk about it too much, but that is one of our plans for smart tiles. Maybe I will. So, I guess I deleted that slide. Okay, so for the mosaic tiles, we were looking at these types of features for what smart tiles should be. And the color denotes when it will be done. So the first version will have like these type of features. Like you can set the quantity, you can make it transferable or not, advisable. And in the future, we want to make it have reputation and stuff like that. But after that, we want to work on things like like computation and storage and bandwidth. So yeah, and expirability. Wow, I forgot that I added that, but that was that's very good, I think. Um, so what storage and bandwidth and computation are they're the building blocks to make programs, like distributed applications that live on the blockchain. And obviously, you can't put all the data, all the programs, and all the data the programs use on the blockchain. That's just not scalable in any way. It's never going to be scalable. So we want to make contracts where you create a contract saying that I want this much space, this much bandwidth, and this much CPU time. And I'll pay this much money if you accept that contract. And then give me the results or whatever. And or you don't even have to do that. You could just run it in a decentralized way. So if you want to create an application that no one can touch, then that's one way of doing it. So that's how we want to do the computation for smart contracts. So instead of having a shared VM where everyone has, I'm not sure how, I should know, but I don't know how Ethereum handles storage. So they give each account storage space for programs, but is that on the blockchain?
Yes.
Yes. Yeah, I thought it was based on Gavin's talk, but I couldn't leave it. I mean, I don't see how that can scale, but I guess it's not very big, but still. But
Why it's not scaling?
Yeah, everything in one blockchain is very big. I think it's you can't scale to the entire world. Maybe fine for a small group of people like in this room. Yeah, so it's what we want to do is not have that model, but really, if you have a program, you just create a contract, and the contract is in the chain, saying that you'll pay this amount of money, and this person does something. But the actual doing is actually kind of managed in a decentralized way. So for example, if you want to have 5 gigabytes of storage, you put 5 gigabytes of data contract there, people accept it, maybe let's say 5 nodes accept it, so that each of the 5 nodes will replicate your 5 gigabytes of storage, and then send the data to all those 5 nodes. And then what you have to do is you can't just trust them and pay them the money and say thanks, but you have to actually make sure that they're doing their job. So you have to have random auditing, and instead of me doing the auditing, if you want to have a decentralized application, you should randomly choose some of the nodes in the network, have them do the auditing, and then use multisig to pay off. So pay off if you're paying 1,000 them for 1 gigabyte per month, then every week you pay 250 them. So let's just, for the sake of example, every week you pay 250. So every week you do an auditing round. Randomly, you'll choose what block height to do it, and then who at that block height is also chosen randomly, so you can't know beforehand. And then if they audit your node, they try to pull the data and then check the hash or whatever that would presumably be stored in the contract. For static data, that would work. Then if it works, they can sign off on the transaction, and then they would get the money for doing their work of hosting. But this is all done in a decentralized way, kind of like storage in a way. In the same way, we want to do computation as well. So you've got this program that runs, and if the program can reference data stored in this contract, so you know what nodes accepted the contract, so you could just pull the data from there. You just have to have like this index stored. And if you pull that data from there and then do the computation, you don't want every node on the network doing the computation. It's crazy, right? So what you do is the same thing. You randomly choose maybe 5 nodes, and then they do it, and then they compare the result. Well, the auditors would get the results from all the 5 nodes and then compare the results. So it would be similar to eigentrust in a way that you're comparing the information across people and then finding out. You just want to say, if everyone agrees, fine, you're done. It's easy. They all did the work. If some people lie, then you just kind of look at what percentage, and you might not want to do just a simple majority, but just you might want to look at like 70% or something. And if it doesn't match, then you randomly want to choose another sample of nodes to do it, and hope that you get more honest people. So doing that, the motivation, to be honest, of course, is you want to get paid, and so if you don't give the data honestly, then you don't get paid. So the details of what types of programs should be allowable is something that's not decided on. We could just take Ethereum's language and use that. But I think what's more interesting, or what might be very useful for this type of approach, is not to have a declarative language, but rather, well, functional would be fine too, but also a rule-based language might be very interesting. So like rules. So in rules, you've got a whole bunch of data it uses the Preddy algorithm. And actually, there's advanced improvements of Preddy as well. And so you've got a whole bunch of facts in the system, and then you assert these facts. So the facts could be just data on the blockchain. And then when you've got, or data anywhere, right? And then once you get some data that matches the pattern that you're looking for, then you execute some rules that will do. Yeah, rule-based programming. Mm-hmm. So that, in a decentralized environment, I think that's really kind of a cool idea. Especially like the idea of having a contract that will monitor the chain for certain events and then do things based on those events. And you wouldn't want every node to run this contract because that would just be really bad. But if you have a few nodes run it and then compare the result, then that could be good. You could run it yourself, of course, but if you want to make a decentralized app, then you want to change that. So for one example would just be gambling, because if you made it centralized, you'd have to buy a license for like $10 million. So if you don't want to do that, you could just easily make a simple game that that just pays out to addresses from an amount that's already owned by an account. So something like that could work. So anyway, so that's all really an area of intense research. So I don't really have any good answer for what the best approach is. I think interesting idea is kind of what Ethereum is doing. So you have a very low-level language, but maybe you can have different high-level representations that map to this lower level. And there's no way I would consider making my own language to do that. I think I talked to Gavin, and he said that if he was to redo it, they wouldn't make their own language. They would use LLVM. So I think that's another good option too. So just so that way you can just compile down from C, and you could have other things on top of that that would also compile down to the common for the files. Yeah. Any other questions? 日本語でも大丈夫です。 研究テーマが、
はい。
まあ全然関係ないんですね。
関係ないですか？
はい。空間情報という分野で、
はい。
人のナビゲーションを研究しています。
あ
まあでも、まあ、共通点としては、あの、ストリートネットワークに人が、まあ、歩いている最中に、まあ、どんな能力があるのか、まあ、道を、まあ、よく間違っているかをまあ、自動的にリアルタイムで判別していますけれども、まあ、それはそれぞれの、まあ、ノードがありますよね、まあ、信号とか。重要な、まあ、よく間違っている信号もありますけど、まあ、それ、グラフの構造によって、まあ、信号の重要性を変えるものとして、まあ、その研究からまあ、ストリートネットワークじゃなくて、取引グラフに交換して、それを実現しました。まあ、いろんなものです。
なんか日本の大学でそういう研究っていうのは、ネームの方は、
はい。
あまり重視されないというか、価値を見出せてもらえない。
いや、絶対そうと思います。はい。それは非常に残念ですね。まあ、こういう、かなり世界を、変える、まあ、変わる技術のに、大学で、まあ、学校とかで、まあ、研究できないのは、まあ、残念と思います。ある大学は、まあ、やってると思いますけど、ほとんど経済学部とか、コンピューターサイエンスは、まあ、こういうものを作ってみようとしてあんまりないんですが、一人の教授にいますよね。慶応か。Facebook グループに。
斉藤先生。
おそらくそうだと思います。これ、どこからですか？
慶応の SFC の。
慶応ですね。はい。先生は、まあ、なんか、こういうものを作ってみてると思いますけど。
新しいコンセプトのアルゴリズム。
詳細、まあ、あんまりわからないんです。わかりますか？
いや、詳細は公開してないです。
公開してないと思いますので、それも残念とも、こういう NEM というようなプロジェクトがオープンソースでやってますけれども、まあ、全部非公開でやるのは、まあ、やっぱり、進み方が遅いと思いますね。いろんなアイディアが入ってこないと。
さっきの斉藤先生の話だと、
はい、
Google でコンセンサスの行方っていうふうに調べると、スライドシェアが出てきて、斉藤健二研究会っていうのが、これが、
まあ、かなり面白いと思いますけど、あんまり、まあ、会ったことはないですね。
今会おうとしても結構開発が佳境だそうです。
今開発されてるんですか、斉藤先生。
そうです。もう作ってるそうです。
そうなんですか。へえ。
なんか、忙しそう。Facebook を見ると。
先生。Okay. Second question. Okay. Yeah. But the general things is fast boosting. It's a side chain. It's a hot topic, and then it's good for the boosting young project. Fast, the project startup project. So it's possible. The one choice for the name is the side chain of the Bitcoin. Do you think?
It's the opposite, I think. So using colored coins, you can put Bitcoin on them. Does that make sense? So you can create a mosaic tile that if you have a escrowed Bitcoin, you can escrow Bitcoin into account, and then everyone can see this account has Bitcoin in it. And then you can put a token on them that represents the Bitcoin, and then you can send it around in 30 seconds instead of 10 hours. Yeah.
The server and the client.
Yeah.
Java.
Yes.
Are there clients in other languages?
Well, it depends on. Well, there's no user. Well, okay. So we have We have an iPhone app that we're working on, and we also have an Android app too. So actually, I have the source for both if you guys wanted to hack something. But that could be fun. Mobile is always fun. And then we have a Python library too that allows you to do signing of transactions and stuff like that using a private key. So that's in Python, but we don't really have any other types of wallets. There is one person who's trying to work on some JavaScript tools. I think you can use like a JavaScript crypto library to do transaction signing using our curve. But yeah, that'd be cool too, because all of it would just be in the browser locally. Then you could even create a website that would be a wallet and you can trust it. And so actually, there's one guy that says that he's working on that, I think. But
The
he,
interface is all JSONs.
yeah, exactly. And it's simpler than that even. You can we have it's not in the API docs, but we have a byte based API as well. So you can just curl byte stream to a node at a certain endpoint, and so you could take the transaction data and that's signed, and then you can just curl that to the server. And that's how the client does. The client doesn't use the JSON API for transaction signing. So it signs the transactions locally and then takes the bytes and sends it to the remote server. So you can actually do cool things like that. You can have a computer that's never been on the internet, and you can sign a transaction, take that byte array, put it in a file, and then take the file on a USB and then put it onto another computer, and then you can send it. So you could have like really insane cold storage. And I know people who are doing that actually, who have never exposed their private keys to a computer on the internet. They just sign it locally and then put it on in a file, and then take the bytes to another computer and curl it. So that's a fun, that's an interesting thing as well. And, yeah. So side chains, yeah, we had the Mosaic API working and documented, then we could easily create a side chain of Bitcoin on top of them. But doing that decentralized is hard because someone has to hold the thing. It would be
to sum them into the name blockchain and pull from the Bitcoin is.
If you did proof of burn, but it would only go one way. Unless you unless you mine.
Stripe storage.
Stripe?
I was just thinking you could have striped storage. So you could have a contract that ensures that each node only stores a part of the blockchain.
Oh,
And because
Ah.
of hashing,
yeah.
and you just have to make sure you know which order what the hashes will contain.
Yeah.
And that would be a way to get around nodes storing it.
Yeah. Well, yeah, we thought about sharding that way. We have a better idea actually. That's just well, actually, it's a different idea. Sharding is good. I actually like the idea. But one idea we had was snapshotting. So just take a ledger snapshot of the balances and send that across the nodes, and they can use that as the starting point. For they don't have to download the entire chain to start with that. But yeah, that's an interesting idea as well. One thing about the server-client architecture is, so on the mobile app, you don't need to have. I mean, we don't run a server on the phone, of course. It's just a client. So we just connect to a remote server. And on the app, you can actually specify what server to connect to. There's a server list. Well, I mean, there's not a list. You can type in IP. But in the future shipping version, we're going to have a list of just kind of trusted servers that are default, and then they'll be chosen by ping. So ping them in the first one to respond or fastest to respond.
What is the difference between the name phone and the iPhone?
So yeah, there's no huge difference. But I like the idea of blockchain phones instead of like 3G network and stuff. We just have all the nodes would just be kind of hotspot type of connections. That'd be really cool. Yeah.
Because
Yeah.
I'm running Bitcoin on SoC.
What's that?
That's a small board computer.
Okay, like a QB or?
Yeah, and you can run Bitcoin just fine.
Yeah, no, we've got people running them on QBs and stuff. As
So
high tunes. But you'd have to not have any breaks in the mesh. Oceans kind of get in the way. But yeah, no, the existing internet infrastructure is actually pretty good. Other people already pay for it, so it's not a huge loss as long as you can just add encryption on top. So, yeah, there's a lot of features in the iPhone that are really nice, but Apple just doesn't put them up. Jailbreak. But it'd be really cool if in daily life you don't have to carry around a wallet, or just just carry around a phone like this. And I was just talking about how you could take a byte array and then curl that to the network. So actually, you could take that byte array, put it on a QR code, and then just show that to the clerk. They take the picture or scan the QR, and then they can broadcast it. So you don't even have to be connected on the internet for you to buy things at a store. So that something like that could be kind of cool. And I was thinking about building something like that, but I don't know. Could that be done in an hour? In 3 hours? Cool. That's one thing that I.
Okay, so yeah, then the first presentation is finished, and then some rest, and then start developing something. Okay, so yeah, thank you, Makoto-san.
はい。